So what we're going to do in this video is we're going to learn how to determine the voltage, or to be able to predict the voltage between any two half cells. All right, and we're not going to do this by physically hooking up those two half cells. We're going to be doing it by a technique called using what are called standard electrode potentials. All right, so to start this topic, I want to go back to the earlier analogy that we were using, which is comparing these buckets. All right, and what we said is, if we wanted to know and be able to predict how water would flow between any of these buckets, we didn't have to hook every single bucket up to each other. All right, we could actually figure things out just by comparing every single bucket to one specific bucket. All right, and that's going to be the bucket that we arbitrarily designate as having a potential of 0. All right, there's nothing special about bucket number 2. It's just the one that we happen to pick, and we're going to say we're just going to compare everything else to that. All right, so by hooking all these buckets up to only bucket number 2 and seeing the way the water flowed, we could come up with this scale, all right, which we're going to call the potential scale, and we can use the numbers in that scale to predict how water would flow between buckets that we've never yet connected. All right, and that's what we're going to do here. All right, so in the same way that we had to pick a bucket that was going to be our reference bucket that we assigned a potential of 0 to, we need to pick some half cell that's going to function like that. All right, and the half cell that was decided on to do that is what's called a hydrogen half cell. All right, or a hydrogen electrode. All right, and the way that works, and I know that this is kind of a crude drawing. There's a better picture of it on page 732 in the white textbook. It takes advantage of this redox reaction. All right, so essentially, 2 hydrogen ions can combine with 2 electrons to make a hydrogen molecule. And the thing I want to focus on is the fact that this is reversible. So if it happens in the right direction, this would be a reduction of these hydrogen ions. All right, but if it happens in the left direction, it would be an oxidation of a hydrogen molecule. All right, so the way this is set up, you have this glass tube here that's got a tube, an inlet on it that you pump, that you can fill with hydrogen. All right, there's a wire going down that goes down through the middle of that glass tube, so this would be sealed here, and then you've got this platinum electrode that is in contact with the liquid up here. All right, notice this is, we've got the same hydrogen electrode set up on both of these voltaic cells. All right, so when the liquid that this is sitting in is acidic, all right, so if it's acidic, it's got some amount of H+ ions. All right, so since you have hydrogen that you supply, hydrogen molecules that you supply here and are in contact with this electrode, and you have H+, which is in contact with this electrode, this reaction could potentially go either way. All right, so electrons could either flow into this and combine with the H+'s to make hydrogen molecules. All right, that would be this reaction going towards the right. And if that happened, we would have hydrogen bubbles that get formed and would bubble out into the solution. All right, but it's also possible that the hydrogen molecules that would be in contact with that electrode, which are supplied by this little gas inlet, could get oxidized. And if that happens, the electrons that the hydrogen atoms lose would flow through the wire this way, and the leftover H+'s would just float on out into the solution. All right, so this is what you call the standard hydrogen electrode. For it to be standard, you have to make sure that you keep, since hydrogen is a gas, you want to keep its pressure at 1 atmosphere worth of pressure, and you would have 1 molar worth of H+ in your solution here. So what we're going to do is we're going to take this half cell and we're just going to hook it up to other half cells. All right, this is analogous to saying, okay, this is like our hydrogen half cell, and now we're just going to hook up these other buckets to it, and see the way things flow. All right. So if we did this with a standard zinc half cell, what you would see is that the electrons would want to tend to flow towards the hydrogen electrode. The electrons would come down here to the electrode. The two of those electrons would combine with two of the H pluses, and that would create a hydrogen molecule, and those bubbles that get formed would just bubble on out. All right, and we could read this voltage here. And something I want to point out, it's not just, this is not just an absolute value. Keep in mind, this is positive 0.76 volts. And what that positive voltage in the voltmeter indicates is the direction. All right, that means that the electrons would be going in this direction here. If the electrons were flowing in the opposite direction, this would register as a negative number. All right, so because we see this positive 0.76 volts, we know the direction of the electrons, and we know the force that the electrons are being pushed through there with. All right, so by comparison, let's pretend that instead of using a zinc half cell, we hook up that hydrogen half cell to a copper half cell. All right, well, what's going to happen? And at the beginning, we don't know which way the electrons are going to flow. I mean, could it still flow towards this way, or is it going to go back the other way? Well, if you hook it up, you get a negative 0.34 volts. And what that indicates is that the electrons are flowing the opposite way. All right. So instead of the electrons going this way and then reducing these hydrogen ions, it's actually a hydrogen atom that's at the surface of that electrode that loses its electrons. The H2 loses its electrons. The electrons go through the wire this way. The H pluses from the hydrogen molecule float out into the solution, and the electrons that flow this way are what create that, allow the voltmeter to measure that voltage. All right, so this would be the reaction that's occurring if you hook this half cell up to copper, but this would be the reaction that's occurring if you hooked up that half cell to zinc. All right. And so what chemists have done is they've done this with every conceivable half cell that you could imagine. All right. So we have this half cell that we've decided this is going to be what we consider to have zero potential. All right. And again, the reason that you would say that it's got zero potential is imagine if you hooked up a hydrogen electrode to another identical hydrogen electrode just like itself. Well, if these two half cells are completely identical, there would be zero voltage. There would be no flow of electrons. And so that's why it makes sense that we call it a zero potential. All right, but it's again, zero is just arbitrary. It's just a number that we've picked so that we can compare it to other things. All right, so we can do this with all different types of half cells, and the data for this is listed in table 24 of your booklet, and here are all the voltages that have been measured. So remember that when you have a half cell, you have both something that could get oxidized and something that could get reduced. All right, and so the electrons could flow either way. All right, so when we're doing this, when we are presenting this data here, you'll notice something right off the bat. First of all, here is our standard hydrogen electrode, and again, it's got a zero potential. All right, and you'll notice that a lot of these things have got what are considered negative voltages, and some of them are positive voltages. All right, and essentially that's a measure of which direction the electrons are going to flow. All right, so to illustrate this, I'm going to go ahead and choose this one right here first to describe. And notice one thing about all of these reactions. They're by convention, just so that we're always comparing apples to apples, all of these are written as what are called standard reduction potentials. All right, so all of these are written as reductions. All right, whether or not the reduction would actually occur, they're written as reductions. All right, so that's why they have them combining with electrons. All right, so let's take a look at this particular reduction right here, and here's its value. So what does that mean? All right, so what that means is that since it's positive, all right, what that means is that this reaction would actually occur exactly as written. All right. So again, if we go up here and compare, all right, if we hooked up a copper electrode to that, all right, what it means is that, so we know that the electrons, when we did this, went this way. So the electrons are flowing into this. We know that it's this copper plus 2 that's being reduced. All right, it's these electrons that are going to be reducing that. So that's what the positive value means, is that if you see positive values here, what it means is that if you hooked it up to a hydrogen electrode, this reaction right here would occur exactly as written. It would occur as a reduction. All right. So since this is the copper here is being reduced, what that means is in the reaction that it's reacting with, it has to be the hydrogen molecules that are being oxidized. All right. So let's compare that to something that is on the list that's negative. And what I'm going to choose is magnesium right here. And so you'll notice that it's got a negative voltage. All right. Remember, all these values are relative to that hydrogen electrode. So what that negative voltage means is that the reaction would actually occur would be the reverse of this. It's going to be the magnesium which gets oxidized. So I go back over here. So again, since that's negative, the opposite would occur with the H electrode. So we can take this and we can just turn it around and show it as the oxidation. And would there be a voltage of that oxidation? So if we're talking about the standard reduction potential, we write it like this. But if we turn it around, it's now a standard oxidation potential for this oxidation reaction. All right. So this is the actual reduction that would happen with the half cell. And if we hooked it up, this would be the voltage that we would measure. All right. So again, what we're going to be doing is similar to this analogy where we've measured everything relative to this particular bucket. And now we can predict what would happen between any of these buckets. All right, so what are the steps for that? So let's say that we connected a magnesium half cell to a silver half cell. Okay, first of all, actually I'm going to put this in the next video so that it's all in the same video.